the proof. Yeah. So if we try to prove that, we can grind for a while. But ultimately, we're going to get down to this case. And what Cock is going to tell us, oops, is that we need to prove that if I add 1 to the current state of backup, that that's less than or equal to the current state of primary. But we know in a hypothesis that backup could be as big as primary. So what's going on? What's the problem here? We're not even proving a spec about the trace, right? So it's definitely, the problem isn't that we didn't relate the trace in the state, because we're not proving anything about the trace.
Should that be, I mean, we kind of know in our hearts, so to speak, that's strictly less than.
Yeah. So what's going on? Why is Cock asking me to prove this, even though we don't believe it can happen?
Is this before the act? Knowledge?
No. That's not a bad guess, though, right? It's like maybe there's a moment before like ascend happens where briefly you could observe a bad state or something. No, the system's actually okay. The spec is totally provable. Primary is always, backup's always, backup's never in front of primary. So what's going on? Why are we in trouble? So what was the problem last time? Remember, the problem last time was that we didn't relate the state to the trace, so our property wasn't inductive. We got ourselves into some world where we didn't know enough about it to ensure that we weren't going to output something that wasn't fresh in the fresh system.
Well, here, when the backup gets that message, it's actually behind the primary.
Right.
The primary has already incremented.
Right. Yeah, so
you can add.
I don't think you can do that. Well, I was already wrong about module types, so.
You'll have to know more of an invariant.
Oh, yeah.
Yeah.
Right.
That invariant will be true.
Right. So it's the same trick it was with fresh, right? For fresh, we needed to relate the state to the trace. Here it's not about the trace. The problem is the network. We don't know anything about the network. Right? In particular, we don't know that the network only has messages in it that were from the primary. Right? So now we're doing this induction. We're off into states that actually can't happen, but our inductive hypothesis isn't strong enough to sort of keep us away from danger. Right? So here's what we need to do. We need to define something a little bit stronger. Right? It's not that. So what we're going to do is we're going to count the number of messages. Oh yeah, it is that. We're going to count the number of messages in the network that are from the primary to the backup, right? And if we add that to the backup, then we should have exactly the state of the primary. And it turns out that is going to be strong enough to prove our property. It's also very specific, right? So this is, perhaps overfitting. Okay, there's a bunch of tactics. You can grind through stuff. That's kind of the big picture. So just to, quickly mention, what have we done? These things called distributed systems, everybody relies on them. It'd be nice to be able to prove them correct. It turns out they're pretty amenable to reasoning about in a proof assistant, right? You need to define the types of information that nodes exchange and that they maintain. And you need to define handlers, so when they get an event, how they update that state and what information they exchange in response to that. Then you get to find some semantics, right, that sort of orchestrate the whole thing and capture our notions of failure, right? Everything from an ideal world where things happen in order, nothing ever goes wrong, to a slightly nastier world where messages don't get delivered in the order they're sent, they can be delayed and reordered. And it turns out we can make much more adversarial semantics, as you'll see in the code. And then once we do that, right, we can prove stuff about these systems. Okay, are there any questions about Verity so far? Proving distributed systems, yes.
So as you mentioned at the beginning, model checkers have been used for a very long time, reasoning about protocols and distributed systems in general.
Yeah.
In your opinion, what are we getting from proof of systems that we don't already get from model checkers?
Well, a smaller TCB, right? So you have to believe in less in order to believe in the guarantees you get from the proof assistant. There's some folks in Tom Anderson and Hank Levy's lab at UW who have found bugs in, there are two things that can go wrong, right? One is that the model checker is depth bounded and it just doesn't explore enough states to find the problem. So they've found protocols this way, right? Where the actual counter examples are just deeper than any model checker that's doing sort of depth bounded search will ever reach. The second problem is that there's a big difference between having a TLA model that's been model checked, even very extensively, and having some C++ code that you run, right? And that's a big gap. And this happens over and over. So there's a bunch of really nice papers. I forget it's like, Paxos made simple, Paxos made fast, blah, blah, blah. And so people have like 10 billion versions of this protocol. And they make these little tweaks to try to get a little bit more performance out, to be compatible with something else. But there's not a TLA model for each of those, right? So in practice, engineers change their implementation, and they have really, it's really hard to know the correspondence. And that's sort of under the level at which people model things. And there are bugs there, right? People make these mistakes. They try to, merge together certain parts of state, and they shouldn't do that because they actually should be independent. Stuff like that happens. So I do think there's a big win to go into the trouble of actually proving systems correct.
But isn't it preposterous to think that the tweaking, the C++ tweaking, is going to be reflected in your formal verification?
We're going to run this.
Yes, but this is not tweaked yet.
Yeah. So then there's a question, right? So the question is, okay, so my complaint against the model checking is that there's a gap between what's proven, or it's sort of model checked, and what you actually run. And then the natural response to that is like, okay, well, are you going to be able to change your system and reprove it, right? How hard's that going to be? I think anybody who's worked on a large verified system, you are very, well, unless you have sort of very powerful automation, you're usually pretty hesitant to change things because it's painful. And that's true, right? That's still a hard problem. I think proof engineering, there are some various approaches to it. I think it's getting better, but I think it's still hard to make it easy to change the systems, so that things are very fast to recheck. Yes?
Can you summarize again, what is the homework you'd like people to try and where to find it?
It's in the Deep Spec Summer School repo under Verity Lecture 1. There's a couple of exercises in these files, but really there's in the README, there's a description. So the point of this lecture, right, is I wanted to convey that it's not that hard to formalize something and start doing this. So when we started Verity, right, Doug and James were taking the grad PL class, and they basically made something kind of like this, but rougher, if you can imagine, right? And Verity grew out of that. So it's not that hard to build models of things that turn into real projects that actually work and can help change the way people think about building stuff. In that spirit, the homework in the README has several suggestions for things to model, right? To get practice formalizing different semantics, to think about the consequences of certain kinds of failure and whether or not they can be handled, in terms of the kinds of handlers that we defined so far. So, and then there's some like listy stuff if you want in there too. It turns out that a lot of the time that goes into verifying big distributed systems is proving list lemmas. So if you'd like, there's some of that stuff in there too, some suggestions for that. Yeah. Okay, folks, thank you very much.